Welcome to the Shape of Space Linear Algebra. In this lesson, I'm going to talk about change of basis for a vector space. Consider an isomorphism from V into itself, which we'll call I, and it's the identity isomorphism. It maps every vector from V to itself. Let S be a basis for the domain and T be a basis for the codomain. So we have, even though it's the identity mapping, it's mapping between two different bases. And then let's matrix A be the representation of S, T with respect to the isomorphism I. And if you recall from Theorem 38 a few lectures back, what this matrix does here is if you multiply it times something from the domain written in terms of the basis S, it gives you something in the codomain with respect to the basis T. But since we're using the identity isomorphism, what we get is actually the vector written in a different basis. So that's kind of very useful for us if you want to change bases. So what I just said here, I've recorded as a theorem, or at least part of this. To convert from the representation of a vector V from basis S to T, multiply V as represented in basis S on the left by matrix A, where A equals this matrix here, representation S comma T, with respect to the identity mapping. In addition, if M times V sub S equals V sub T, then M is a change of basis. So basically we have a uniqueness here. The first part of the theorem we proved above. Second part of the theorem, we know that with respect to basis S and T, the matrix M represents a linear transformation whose action is to map each vector to itself, but as expressed in a different basis, and therefore M equals representation S comma T I, and that equals A. So we have uniqueness. Let's look at an example of our theorem from the previous slide. We're given two bases for R3, S and T. Our task is to find a matrix A that maps a vector represented in terms of S to a vector represented in terms of T, where the vector comes from R3. So we let I be a mapping from vector space R3 to itself, and it's the identity mapping. Let S be the basis for the domain and T be the basis for the codomain. Then we take I, evaluated each one of these vectors, and of course it's the same since it's the identity, but then we need to represent each one of the vectors of S in terms of T. So the first vector is just 0.5 times the first element in T, and then 0 times the second two. The second vector is 2 times the second vector in T, and 0 times the other two. And then the third vector in S is 0.5 times just the third vector in T. So that is pretty easy to do the mapping here. And then the matrix A, by definition, is formed by taking I of S sub 1, S sub 2, S sub 3 is the three columns. So we put this in here, this here, and this here. And that's our answer. We can check it out. We can multiply A times some example vector V sub S, which I have here. We multiply that out, and it should give us V represented in terms of T, which is this result here. And then we can check it two different ways. We can take V sub S and write it in terms of the standard basis. So it would be 100.5 times the second vector in S, and then 3 times the third vector in S. And when we compute this, we get 1, 1, 3, and this is V represented in terms of the standard basis. And then we can take this output here and expand it out and see what that equals. It should be the same in terms of the standard basis. So we get 0.5 times 200, 1 times this vector, and then 1.5 times this vector. And we do the computation and we get 113. So when we expand the vector v in terms of the standard basis, starting from both the basis s or the basis t, we get the same result, which is what we should get. So we checked out here. We have a couple of theorems. Matrix affects the change of basis if and only if it is non-singular. I'll give you a link to a proof of this. It's actually a book, an online book. And then the next theorem, a matrix is non-singular if and only if it represents the identity map with respect to some pair of bases. So from the theorem 44, a matrix is non-singular if and only if it represents a change of basis. And then from 43, we know that that's with respect to the identity map. So this theorem 45 follows from the previous two theorems. It's possible to convert from a representation of homomorphism F from V to W, where you're using bases S1 and T1, to F where you from V to W, so it's the same homomorphism, but you're using different bases. So S2 for V and T2 for W. As shown in the figure, there's two ways to determine the matrix representing F that maps a vector V represented in S2 for vector space V to a vector W represented in T2. So the two ways are: one, directly compute the representation of F from S2 using bases S2 and T2. That's this way here. And then there's a longer way, at least a more involved route. You first change your vector V from the basis S2 to S1. Then you use your initial representation to go from the map V sub S1 to W sub T1. So that's using the bases S1 and T1. And then you map from W from basis T1 to the basis T2. So you can go either this long way or this way here. And I've written down the two equivalent ways here. This is this one here, and then this is the path here. And you may wonder why I have this in reverse order, and that's because these representation matrices, these are all matrices, they're multiplied on the left of the vector. So if you start with V sub S sub 2, then you first apply this mapping, go from here to here, and then you apply this mapping, and then you apply this mapping, and that gives you the same thing as applying this to V sub S sub 2. So going two different ways, you get the same result. Now I'll give you a bit of explanation of why would even bother doing it this way in a few slides, but just accept for the moment that there's two ways, at least two ways of getting a representation of F with respect to bases S2 and T2, given that you've started with a different representation using two different bases. This slide is just a recap of what I proved on the previous slide. So theorem 46, to convert from matrix representation of F with respect to S sub 1, T sub 1, to the matrix representing F with respect to bases S sub 2, T sub 2. We have two different ways of doing it. One is the direct path here, the other one is here, here, and here, which which I've written out here. And again, the reverse order is because you multiply all this on the left of the vector. So first you apply this to v sub s2, and then this, and then this. And so that's the two different paths. So nothing different here from the previous slide. The next example involves a little bit of complex analysis. I'll give you some background here, but I do assume the reader has a basic knowledge of complex analysis. If not, I'll give you a reference to a book I wrote. It's freely available, and I'll point you to this section that gives an intro. You really don't need that much to understand what I'm going to present here, but let's go into the background. So in the complex plane, numbers, effectively two-dimensional vectors, can be represented in polar coordinate form using something known as Euler's formula. So we have that here, r e to the I theta, where I is the imaginary number, square root of -1. And the formula expands this out in terms of the cosine and the sine. So the r cosine theta is the real part, and then r sine theta is the imaginary part of the number. R is the length of the vector, and theta is the angle the vector makes with the real axis, assuming the vector's tail is at the origin. So for the discussion here, we're going to let r equal 1, and it simplifies things a little bit. We'll take a vector v equals e to the I theta, which, since r is 1, that equals cosine theta plus I sine theta, and we want to rotate it by an angle alpha. So using the polar coordinates, all we need to do is multiply by the e to the I alpha, and we get e to the I alpha plus theta, just adding the exponents, and then we can use this formula again to expand this out. And then using the formulas from trigonometry for the sum of two angles, we get this here for the cosine of theta plus alpha, and then the sine of theta plus alpha is this expression here. So this gives us the formula for rotating the vector v by an angle alpha, but we can write that in terms of matrix multiplication. So our matrix A is here, and our vector v, we're writing it as a column vector here. So this is the real part, and then sine theta is the imaginary part. And then when you multiply the matrix times the vector, you get this result. You notice this top here, the row 1 is equal to this, and then row 2 is equal to the imaginary part. Okay, so we're going to use this on the next slide in an example, and we're actually going to take alpha equal a particular angle, but we'll get to that in a second. Okay, let's get to our example. So we have a function f, a homomorphism from R2 to R2, defined by pi over 2 counterclockwise rotation. And we know that we can do that by multiplying by a matrix A from what we computed on the last slide. We just need to plug in pi over 2, or 90 degrees. The cosine of pi over 2 is 0, and the sine of pi over 2 is 1. So we get this for A. And note that A was defined in terms of the standard basis for the domain and the codomain on the previous slide. And our problem is to find another matrix to accomplish the same rotation, but using the basis S for the domain and the basis T for the codomain. And we know from our previous discussion there were two ways of doing that. We can directly compute the representation here, this matrix, using S and T directly, or we could take this other path. We can convert the vector v in terms of S to the representation in terms of the standard basis, and then use our matrix A here, and then convert from the result W, which is in the standard basis, to the basis T. So we'll show both ways on the next slide. So on this slide, we're going to take the longer approach, which I'm pointing to here. And I also copied the two bases and the matrix A, so we have that to refer to. All right, so first going this way here, what you need to do is evaluate I for each one of these, and then write it in terms of the basis E2. So that's pretty easy because this is the identity mapping. So if you map these with the identity, you're just going to get 1, 1, and 0, 1. And then when you write it in terms of the standard basis, you're going to get 1, 1, and 0, 1. So that gives us the well, it gives us this here, which I'll eventually plug into this formula down here. Then we already have A, so there's no work to do there. This was almost automatic, no work to do here. Now here's a little bit harder because we have to convert from the standard basis to T. And there's a couple of ways of doing that, which I mention here. For the last leg of the journey, we could write E2 in terms of the basis T, or we could go in the opposite direction. In other words, we could do what we did here and just take the matrix 0, 2, 1, 0. In other words, if we wanted to go in this direction, and then going in this direction is just the inverse of this matrix. So that's what I did. I took this latter approach. I took the inverse of this. I didn't show you all the details, but if you work through the details, you're going to get 0.510. And so now we have all the pieces we need. Here's our formula. We have the representation E2 with respect to T, then our matrix A, and then representation of S, comma, the standard basis with respect to the identity mapping, and that goes here. And so we multiply, and I should mention here that multiplication of matrices is associative. So we could have done these two first, or these two first. I decided to do the first two first. I multiplied these two together, and I got this. And then I multiplied this times the term on the right, and we got this here. So this is our transition matrix going from VS, V is represented in S, to W is represented in T for our function F that rotates by pi over 2. Now we're going to do this directly, and we would expect to get the same answer here, 0.50 minus 1 minus 1. Okay, so I'm going to go to the next slide and we'll do this computation. So let's go in the other direction, this direct computation. We need to take f of each element of the basis S, which we've done here, multiply by A, which I've copied here for your reference. So we get these two vectors. These are in E2. So we need to represent each one of these in terms of T. So minus 1, 1 in terms of T is this here. It's 0.5. This will give you a 1 on the bottom, and then minus 1 on top. And then minus 1, 0 in terms of T. We don't even need this here. We just need to multiply minus 1 times this. Get this here. So just putting these as the columns in our representation ST with respect to F, we have 0.5 minus 1, 0 minus 1, and that's what we got from the previous slide, going this way around. So as an additional check, we can take an example. Let's take a vector 1, 1, write it in terms of the basis S, multiply it by this matrix here, what we've computed, and then convert it back to E2. Okay, so we have 1, 1 in terms of the basis S. that's 1, 0. It's just 1 times this term plus 0 times that term. Then we multiply it by this here. We get 0.5 minus 1, but this is in t, so we basically going from, we started here with this vector, but we went down to how it's represented in S. We multiplied by this matrix, and then we have something in terms of t, but let's convert that to the standard basis. So we have 0.5 times this is 0, 1, and then minus 1 times this is minus 1, 0, and that you add those two together and you get this here. Okay, so that's going here, 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 and then here. Then we can just go that way. This is the same result as applying our matrix A times 1, 1. And as you can see, when you multiply, you get minus 1, 1. So you get the same result. So we've done a check to make sure that we've gotten the same answer for at least one example vector. If you recall earlier, I mentioned that I was going to give some rationale for going along this more, what appears to be this longer path rather than going directly. So what we have in this picture is we're given A, so we know how to do some mapping of our function f to a matrix from the standard basis to the standard basis. And we want to switch to the different bases, S for the domain and T for the codomain. In other words, we want to find this representation of f. And if you look at the two ways, it's actually more computation going this way. And I explained it here in this paragraph. So let's go through that. As we saw in the example 2, going from here to here was just taking the basis vectors for S and putting them into a matrix. So there was really no work there. And we're given A, that's the starting point. And then going from here to here, it's the same idea that we did before. We take the inverse of going from here to here. So we put the vectors from T into a matrix and then take the inverse, and that'll give us this direction. So really the only computation is one matrix inversion to do this entire path. Now going this way here, as we saw in example 2, we had to solve two systems of equations. We had to take the f of each vector in S and then write it in terms of t. But if you have 10, for example, if you have 10 basis vectors, and now you have to do solve 10 systems of equations, each with 10 unknowns, and that's far more work than this other approach going this way here. So as the number of basis vectors gets larger, it becomes really prohibitive to go this way. Assuming that you already know what A is, you can just do this simpler or less computational intensive path to find this matrix. Okay, so hopefully that gives you some understanding why we bothered to talk about this other path here. On this slide, we define equivalent matrices. Given rectangular M by N matrices A and B, they're said to be equivalent if B equals P times A times Q, where P is an M by M invertible matrix and Q is an N by N invertible matrix. That's the definition. Then we have a theorem. Equivalent matrices represent the same linear transformation, F from V to W, under two different choices of basis pairs for vector spaces V and W, where P and Q are the change of basis matrices for W and V respectively. So to prove that, we have a number of assignments, these bullet items here, and then we will use 46 to put this together to prove our statement. So to prove the above statement, let F be a linear transformation or homomorphism from V to W, where V and W are vector spaces, and then S and S prime are the bases for V. So we're changing from S to S prime, and then T and T prime are the bases for W. Then we let A be the representation of F with respect to S and T, and B be the representation of F with respect to S prime and T prime. We let Q be the change of basis matrix from S prime to S. So in other words, Q equals this here. Or we can, to write this out, for any V in any vector V in vector space V, we have V sub S equals Q times V sub S prime. And then let P be the change of basis matrix from T to T prime. Notice we're different directions here. So P equals representation of the identity mapping from with respect to T and T prime. So for any W in vector space W, we have that W sub T prime equals P times W sub T. And if we put all this together, we have B equals this. That's by definition. And then this part here comes from theorem 46. We're just plugging in the pieces that we need here. And this is P. Right, that's P, this is A, and this is Q. So B equals PAQ, meeting the requirements of this statement here. Theorem 47 makes use of the concept of equivalent matrices. Any m by n matrix of rank K is matrix equivalent to the m by n matrix that is all zeros except that the first K diagonal entries are 1. The matrix described in the proof is shown in the figure below. So that's what we're saying here. You have a K by K identity matrix up here, and then these capital Z's are all zeros. What I'm going to use is to prove this, I'm going to use the concept of elementary operations represented as matrices. I talked about that several lessons back towards the beginning of the series of lectures. So hopefully remember that, or if you don't, you can just look up elementary matrices or elementary row operations, and you'll, like on Wikipedia to refresh your memory, or go back to the previous lesson. So in terms of the proof, we first reduce the given matrix by a series of elementary row operations, represent the row operations as multiplication by elementary matrices on the left, and collect these elementary matrices to form P. So these elementary matrices are invertible, and if we just multiply them together, we get an invertible matrix. So that gives us P. Then use the leading entries to do column reduction, and finish by swapping the columns to put the leading ones along the diagonal. So representing the column operations is multiplication by elementary matrices on the right. So again, we're going to form an invertible matrix. We'll call that Q. And then those two together will give us our proof that we have a matrix that's equivalent to this here. So in other words, our initial matrix is equivalent to a matrix in this form here, because we found the P and Q that will multiply times our initial matrix give us this matrix here. I'll show you an example in the next couple of slides to show you how this works. Then we have another theorem. Matrix equivalent classes are characterized by their rank, i.e. two matrices of the same size are matrix equivalent if and only if they have the same rank. That follows from this theorem here, because we can put them into this format here, and then they would be equivalent. Okay, so let's look at an example. So on this slide and the next, I have an example of our Theorem 47. Start with the matrix A, and then we'll find the matrix P and Q to get it into this form here. Now it turns out that A is of rank 4, so we're going to get a 4 by 4 identity matrix, and that kind of obviates the need for these Z's here, just to kind of warn you in advance. So we first row reduce A to determine the matrix P that was mentioned in the proof. And the right-hand side of the calculations keep track of the row operations. So when we work through this, we're going to, what we end up with is going to be our matrix P here. Okay, so we take A, we put it in here, we put in the identity here, and then we do basically the same operations that you would do to find the inverse. Take twice the first row from the second, and then subtract the first row from the third and fourth rows, and that gets us here. Then we subtract the second row from the third to get here. Then I switched row 3 and 4. It just makes it a little bit easier to get a 1 further down. I didn't have to do that, but I did. So going from here to here, all I did was switch row 3 and 4. Then I subtracted row 3 from row 4 to get this. Then I subtracted 1 times row 4 from row 3 and 3 times row 4 from row 2 to get rid of the 1 and the 3. Then we want to get rid of the 1 and the 2 here, so we take 1 times the third row from the second and twice times the third row from the first. Leaves us here. So this is our P. I could have continued to get rid of this 1 here, and then we would have had no Q, or Q would have been the identity matrix, which isn't very interesting. So I stopped short a step here, and we'll remove this 1 using a column operation on the next slide. So repeating myself here, we could have continuous row reduction, which would have resulted in the matrix Q being the identity. In other words, nothing to make use of there. To make the result a bit more interesting, we finished the reduction with an elementary column operation. Get rid of this, so we take 1 times column 1 and subtract it from column 2. And again, we track that with an identity matrix here, and we get this matrix here. So we have, putting the results together, we have P equals AQ, P times A times Q equals this. So this was P from the previous slide. This was the matrix we started with. This is our Q, and it equals I. And as I alluded to earlier, because A was of rank 4, these Z matrices disappear because they're only there as filler. So if A, for example, was of rank 3, then we would have ended up getting a row of zeros and a column of zeros, and we would have actually had something to put in here. But in this case, we did not. So it still has the format. I mean, it's just that it's only this upper left part that we have. Okay, so that's it for this rather long lesson. I have still quite a few more lessons in the lecture series on linear algebra, so stay tuned.